Hello and welcome to Digital Signal Processing or DSP complete course. So, first of all, this course covers the theory of signals, signal types, mathematical signal processing, signal analysis and modification. It's one of the essential subjects in electrical communications. It involves the application of calculus and linear algebra. It also uses complex numbers to represent a signal, such as the residues, poles and zeros in complex numbers, Z transform, Fourier transform, digital signal conversion from analog to digital, like sampling, quantization, and coding, etc. There are many subjects also related to that. So what is DSP? The variation of physical parameters or parameter values such as temperature readings, sound, images, air pressure, and other variables is of analog nature. We cannot digitally process and quantify these values in their analog form, so we need to convert them into a mathematical form, which is a digital numeric form and quantifiable form that we can count, that we can process, that we can work on. This is where DSP comes through to convert a signal to a set of numbers processable by a computer software. Once any signal becomes a sequence of numbers, it can then be analyzed, measured, processed, altered using mathematical equations. An example for that, an audio track of a song is a set of amplitude values placed in sequence in the progression of time. We start with audio capture using a microphone. So, for signal capture at first, microphones have an external membrane like the ear's tampon. They vibrate due to the fluctuation of air pressure around them, carried by the energy of the sound energy, which is the sound wave or voice. This tampon is connected to a coil that swings in the same frequency of the sound, creating an inducted electrical current, having the same properties, which is the same amplitude, the same pitch, and the same frequency of the incoming wave, of the incoming sound. The generated electrical current is too weak that it needs an electrical amplifier to boost its average power, and we end up with an analog signal, like the one presented below here, having an infinite number of amplitude values changing in respect of the time variable. An example for that. So an audio track of a song is a set of amplitude values placed in sequence in the progression of time again. We start with audio capture using a microphone. We've spoken about that. So at first we need to take samples. So in the sampling process, what happens? Analog signals have an infinite number of values that need to be scaled down or reduced to a finite number before digitization. And coding, of course. This is done through a process called sampling, where we take periodic samples from the signal in a constant pace, as you see down below, where these samples, from the signal that are taken in a constant pace during constant repetitive time cycle t, are then reduced again into discrete numbers, but we haven't gotten to that point yet. So we take these samples, and then from the sampled cuts, we choose only one value, usually the average one in the middle. Let's check it. So the sampling period, which is t, meaning how often or the duration of the sampling cycle. So during 1t, we're taking a sample. Now, this is different than the duration of the sample itself. That's the sampling period. 1/t gives you the sampling frequency as well. Alright? So the sampling period is t. That's the duration in which we take one sample. Of course, the duration of the sample itself is small t. That's the sampling time, or the duration of one sample. And you see here, it's a repetitive cycle. That's a constant cycle. So each t, we take one sample having a duration of small t, let's say. Alright? So that's the sampling period. And that's the duration from here to here of one sample. Now, the way samples are clipped from the main signal is by multiplying the main signal with a square signal, as you see here, having an alternation of +1s and zero values using a multiplicator circuit, which is not showing here, but let's say you have a multiplicator. Its symbol would be a circle and an X within that circle. One of the input would be the main signal, which is the original signal, and the other input would be the square signal, which is an alternation of ones and zeros. And as you see here, each time the signal is multiplied by 1, it is taken, the values are kept, but when it's multiplied by 0, we clip it, okay? We remove the values that are multiplied by 0. So the parts multiplied with 1 remain, but the parts multiplied with 0 will have 0 values and they are removed. After that, one discrete value of each sample needs to be taken. So after that, one discrete value is taken from the sample, like in the middle, at the beginning, depending on the sampler type. That's the value to be quantized and coded later, which we will explain. By the way, there's also a premise here that needs to be mentioned, that as you see here, we have a loss of many important values that construct the signal. Actually, this is not a good sampling, but here we lowered the frequency of the sampler, which is the frequency, okay, f being the inverse of the period. So the frequency of the square signal here is relatively low. It needs to be high, meaning the number of squares need to be much higher in order to lead to a more accurate sampling process, because here we have the loss of many important values. Usually, the frequency of the sampler, that's the theory of Shannon, f should be at least 2 fm. So let's check it here. So the frequency of the sampler should be at least equal or greater than 2 fm, which is twice the frequency of the message, which is the frequency of the original audio input. All right, that's Shannon's law, because less than that, as we see here in the example, we would have like a less adequate sampling with a loss of many values. So it would lead to a signal that is not accurate during restoration. So what are the types of samplers that we have? First of all, you have the uniform sampler. The uniform sampler extracts a value of samples at fixed time intervals. As an example, it takes the first value it encounters at the beginning of each sampling period, like we see here, all right, and adopts it for later. Now, the application is for audio. Most analog to digital converters, ADC, use it, and it's very fast. It doesn't require any processing. Now, as we notice here, you have the sampler taking the first value of each sample, all right, the first value it encounters, regardless. This is how it works. And of course, it abandons the remaining curve. The second type of sampler is the random and non-uniform, which is used, by the way, for seismic data collection and biosignals. So discrete values are taken at a random time within the sample duration, not sampling period, which includes a mute. This is being this area here, okay? So without like the areas that are void, that are clipped. So how it works, again, it takes samples randomly from the entire sample duration. It can take it from here, from here, from here, from here, but one sample, one discrete value of each sample. That's the most important premise, all right? And it's not a fixed duration, meaning that unlike the previous slide, where we've taken only the first sample we encountered, which is a fixed extraction of samples, of discrete values of the samples, here we are taking the samples, or the discrete values, sorry, of the samples from random times, from random location within the sampling duration here, not the sampling period, the sample's duration. So you notice at times we are taking the discrete value of the last part of the sample, or in the middle, or at the beginning or less than the beginning, or less than the middle. Here it's almost at the beginning. All right. And by the way, this is for usually used for radar signals also. Average sampler. Now, how does it work? Discrete values are taken as the average value of the sample, meaning mid-level point if you have like a climbing or plunging curve. So now it's relatively slow, requiring CPU power to calculate the average level of that point throughout the curve. It takes multiple mini sample values and averages them to pick the one in the middle, or the one having the middle value, not the one in the middle. So in other words, you see here this climb, okay? So you have like, it averages the values from left to right, okay, the amplitudes, and it takes the middle value, okay? It's almost like in this area here. Here you see, okay, it's almost in the middle because it's a uniform descent curve, so the middle value would be here. Here it is not the middle, but a little bit up because you have more values on the peak, correct? And here also because you have more value that are higher than this lower slope, so the middle would not be the trough, but rather a point behind it, etc. Quantization. The discrete points that were taken by the sampling process can still have an infinite unpredictable value or values to them with fractions, for example 10.2, 10.33, 10.234, so they need to be adapted to a fixed and limited scale of possible numbers that can then be coded. The process is called quantization. It involves reducing infinite possible values to a reduced and limited number of values that belong to a fixed range with predefined possibilities. Whenever a value is not exactly equal to one of the numbers on the scale, it needs to be snapped to the closest value level, which is either up or down, above it or below it. Now, if it falls in the middle, depending on the algorithm, of course, it would either snap to the upper level or lower level, or randomly up and down. And by the way, in such case, you would have the maximum error margin. Why? Because it is at the highest distance from the upper level and the lower level. All right, so the margin of error would be high. So for example, here you see this point is or has a value of 43.123. It is the closest to level 45, which is the one above it than the one below it. All right, so that's why it would be updated and the point snaps to the upper level and it takes 45 as its value instead of 43.123. And of course, the lowest the distance is between the upper and lower value, the highest the resolution would be. Why? Because we would reduce the error margin, all right, by reducing the distance between these two possibilities. Now, in such case, you see here, by the way, that's why it snapped to the level 45, because D1 is less than D2. So this point having the value 43.123 is the closest to 45, to the upper level. So it's updated by 45. After the quantization process, the discrete values taken from the sampling process are updated from the prefix values, or by the prefix values rather, from the quantization or quantification scale. So as you notice here, you have the older position, which was in between the predefined values of the scale. So these points were updated by the actual values that are among these levels within the scale. Why? Because we need to have these predefined values, because the coder cannot code unlimited values. It needs to stick to these values that are predefined for the amplitude. So for instance, here it was snapped to 45, here to 60, here to 35, 20, it was like above, and it was snapped below. It was around like 22 or something. And here it snapped up from 16, 17, something like that, to 20, etc. All right. So as you see here, as we mentioned, this point that was at distance D1, which is less than D2, was snapped to the upper level and was adopted as 45. So it lost its older value. This is why you get some noise, some slight distortion within the signal, because the values are no longer exactly the same. That's why we need to reduce the distance between levels to have or to obtain the maximum resolution. By the way, the number of levels are also equated with the resolution. So when you have, instead of 20, 30 levels, 100 levels, the resolution of the song or the sound would be much higher. It would be like the closest to the real original signal or original value of the signal at each point. So after the quantization process, the discrete values taken from the sampling process are updated from the prefix values from the quantification scale. The series of sequential values we get in this example is 45, 35, 60, 20, 20, 40, 40. All right, these are the values in sequence. Now we need to bear in mind that for an adequate definition of the signal, we should have used a sampling period, as we mentioned before. Smaller sampling period, meaning that the samples should be much closer. We need to minimize the gaps between samples. This is what we're talking about, to have a more adequate signal, adequate sampling process. Another thing to be noted is that the number of quantization levels determine the resolution of the signal or accuracy of description of the signal, what we mentioned before. This is the difference between an audio clip of rate 128 kilobit per second on your computer and one with 238, actually 360 kilobit per second. The latter is more clear and accurate and closer to the original source of the sound. So because it has a much larger number of sampled values. The gap areas where no samples are being taken are replaced with inaccurate values. Okay, why? Because they are being approximated. Let's say you need to draw the curve between these two values here. Okay, you have no idea that you had this bump between the two during the reconstruction of the signal. So you will try to approximate the original value. However, the signals that would be drawn would be like this. Okay, I mean, it won't be the exact original signal, so you would lose some of the original values. This is it will represent some kind of distortion in the signal, and what you would get instead is some form of erroneous values that will be as noise within the signal. All right, so these values that fall in place other than the original location where the curve was passing in the original analog signal when it was recorded present themselves as noise. Why? Because they are not the exact values. So they would present as some type of distortion due to the inaccuracy of their location during the restoration of the main signal. Now the gaps, okay, are replaced with inaccurate values. Okay, they represent themselves as noise. We've already mentioned that. But not only the gap fillers, as we see in the illustration of at the bottom right here, what you see is that the quantization has snapped a value, and we've already talked about that. The quantization process has snapped the value to a different level than its original level. It was at 43.123, but then it was snapped to level 45. So it lost some of its original value. That's why the larger the number of levels is, the smaller the error margin will be. Why? Because these levels would be stacked upon each other. They would be much closer. So the error margin would then be reduced. Why? Because the maximum distance of error, which would be half of the distance between 45 and 40, would be narrowed down. So you would reduce the error margin. You would narrow down the error factor. Again, maximum error margin is when the sample falls right in the middle, which is the middle of the distance d. So maximum error margin would be d divided by 2. Why? Because in such case, you have no idea to reconcile where the original point was, because it happens to be at the mid distance from the upper and lower level. So it needs to be snapped to either of them, but in either cases, it is a little bit like it's much further. Meanwhile, for this example here, it is around 43.123. It is the closest to 45. Okay, so you didn't actually lose that serious amount of accuracy. Meanwhile, when it's in the middle, you have the mid-distance error, okay, which is the maximum error excursion, okay, equivalent to d over 2. Coding. Now, of course, here we're not talking about coding with compression, all right? So we're considering coding without the factor of compression, which is usually used to reduce the amount of data that needs to be transmitted or stored if you're storing a file on a hard drive. So the values that we have should be coded to binary before transmission or storage. In this scenario, we are not considering compression, which reduces the amount of data to be transmitted or stored and reduces the size of an audio file on the hard drive, just to make it more simple for the explanation. So how to get the number of bits required to code all the possible values that we have without, of course, afterwards performing a compression, only straightforward coding. So the number of all possible values for this signal below is the entire range from 10 to 65, right? Which is, not only the values that happen to have been used. No, we're talking about the scale of all the values within the scalar. Okay, so these are all the values from 10 to 65, all the possible values, not the ones that we used. Okay, which is equal to 65 minus 10 divided by 2 plus 1. That would give you 12 possible values. Okay, this is the formula. If you count them, you end up with 12 possible values. So it is the difference between 65 and 10, all right, divided by 2 plus 1 equal to 12 possible values. So the values are the following: 10, 15, 20, all the way to 65. If you count them, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So how many bits do we need to code 12 possible values? To get all the possible values from a number of bits n, we calculate 2 to the power of n. So, for example, for 3 bits, how many combinations can we get? It would be 2 to the power of 3, which is 8 possible values. If you want me to count them, these are 000, 001, 001, 011, 100, 101, 110, 111. Okay, these are 8 values. All right, let's check now how many bits are the minimum needed to code these 12 values that we have. All right, so 2 to the power of n is equal to 12 values. How many bits should we have at least to code 12 values as a minimum? It's not necessarily exactly 12. You may still have an excess. All right, so 2 to the power of n is equal to 12. Okay, we know that 2 to the power of 3 is equal 8, less than 12. It's not sufficient. But 2 to the power of 4, that's 16. That's great. Why? Because 4 bits can give you 16 values greater than 12 values. So use the 4 bits for the coding of 12 values with 4, symbols extra. Okay, with an excess of 4 possible symbols. And as you see here, you have 0, 0, 1, 1. Okay, these are 4 bits. You would get at least 12 values. Actually, exactly 16 possible values can be coded via 4 bits. Mathematically speaking, how to get the value of n, which is the number of bits needed to code the set of values of a scale. So the total number of values on a scale is, let's say, okay, it is 32. Okay, the total number of values that need to be coded. We know that we place 2 to the power of n is equal to 32, but how to mathematically get the value of n without the trial and error, without starting to try numbers until we get 32 or a number greater than 32? First of all, 2 to the power of n is equal to 32. Second, we place ln, Neperian log, around each value, each element to the left and to the right. All right, of the equation. So ln2 to the power of n is equal to ln32. Then what we have is ln2 to the power of n gives you n ln2. And by the way, 32 is actually 2 to the power of 5. So n ln2, if you know log, because anything powered on a logarithm is multiplied, the power is multiplied by the ln from this side. So n ln2 is equal to 5 ln2, and you get rid of ln2. So n is equal to 5. This is how we get it mathematically. Great. Signal reconstruction. Signal reconstruction follows the reverse route, meaning that we need to go in reverse. We need to undo whatever has been done. We go in the reverse route to restore the signal. In other words, the binary blocks are decoded to restore the actual amplitude values that belong to these binary blocks, correct? Then amplitude values are drawn over the scale. Of course, we cannot restore their exact original values. They are based on the quantizable values that we've gotten through quantization. So after placing them on a scale, we need to establish a curve or like a line between them that will depend on the mechanism of restoration or the algorithm of restoration. After the approximation curves, usually we use curves because they are the most adequate in re-establishing the signal. And these curves are approximated between subsequent values to reform the signal. We note that the reconstruction won't restore the original signal at 100%, of course, because the accuracy refinement is determined by the number of values that were taken from the sampling during the transmission. That's on one hand. On the other hand, the values themselves have been scaled or adapted to the quantization scale, correct? So they are not the exact values, at least in most cases. And the number of quantified numbers that will affect, or which is how large the quantization scale was, that will affect the resolution of the restored signal, or how close the restored signal is from the original signal, in other words. What are the reconstruction types? Now we get to how the reconstruction would be. So for ideal reconstruction, that was according to Joseph Fourier, and it was stated that any random continuous signal can be made up of a sum of sine waves or cosine waves, the same thing. So ideal reconstruction uses the cardinal Sinc, cardinal sine wave function to recover the signal from the set of samples that were taken. And of course we have a form to the discrete signal, not necessarily the continuous, but it works both ways. So the output xt is represented by the function below, and it's an ideal. Xt is equal to sigma n going from minus infinity to plus infinity. Of course, we change the domain according to the length of the signal. Xn multiplied by sine wave t minus nt, t is the period, okay, divided by t, and it would give you a response for that signal. All right, and n is the position of each symbol. Reconstruction types. Okay, you have another type, which is the zero order hold. Zero order hold maintains the sample value constant in time until the next sample value comes up, which is common to digital to analog DAC converters. It is fast, it doesn't require processing power. But the disadvantage, of course, is that it introduces significant distortions and artifacts to the signal. You notice here down below that we have the first value of the signal is this. It keeps on going until it changes. So it goes up once another value has been found. And then it keeps on going to the same level until it's updated. So it's like squared. It has a square form. It's not adequate, and it represents so many distortions and artifacts. Artifacts are like these noise, images that you see on your TV when the reception is not well. These are the artifacts, meaning that they are alien introductions to the original image that distort the quality of the image. This is what artifacts means. That mosaic effect, that crackling in the image, which can also present itself in the sound, in a different way of course, is called an artifact, which is something strange to the original signal, and it distorts the original signal. So this type of restoration, which is zero order hold, it's not accurate, but it's very straightforward and fast. This is one of the advantages. First order hold, FOH, it performs linear interpolation between adjacent sample points, which is suitable for signals with low change frequency. When you have a low change in the frequency, it's very suitable. Now the advantage here is, instead of guarding the same value throughout an interval, it interpolates between two subsequent values, meaning that, in other words, it draws the line between each two subsequent values. So here you have, for instance, this value and then this value. Interpolation means it draws the line between them. So y equal ax plus b, you get y and x through the coordination or the coordinates of these 2 points, and you get what? A and b to get or to form or to establish the line equation, the equation of the line that connects these 2 points. This is how it actually works. So it's better than zero order hold, but still present artifacts and signal distortion. It's not practical for signals with swift changes. Why? Because the error margin would be very high. Meanwhile, if you have slow changes in the signal, here it's almost adequate, okay? It's like satisfying to a certain extent, because the shift or the changes between different points, the signal is not fluctuating drastically, so it kind of get us good results. Polynomial interpolation. Now, in other words, it forms cubic SP lines. How it does that? It uses higher order polynomials, which are curved signals like x2 function, nonlinear curves to represent the signal or to connect subsequent points together to fit a smooth curve between sample points. As you see here within this graph, we have a very good representation of the signal. Of course, it's not 100% accurate, but it's much better than zero order hold and the line interpolation method. So this mechanism is more accurate for signal restoration, but computationally intensive. Why? Because it's forming a curve between 2 points, so it has more computation requirements, more than interpolation and zero order hold. Now, computationally intensive at the same time. Drawbacks, it may overshoot the value, meaning that when you have a curve that has been like you have 2 points and the curve is more bumpy than the required thing, so you might overshoot the original value in between because the curve is too high or too low. That's put it simply. Band limited interpolation with windowed Sinc. Sinc are wavelets actually. This is what Sinc is. We've seen it in the other slide. These are wavelets, and they are some of the best thing to represent a signal, by the way, because it's Fourier's law that any random signal can actually be converted to a sum of sine waves. It approximates ideal Sinc interpolation using a limited trunk of Sinc. This approach produces a good accuracy with less computational power requirements. That's the advantage, okay? Because you're not like processing to obtain a curve. This is the wavelet, which is Sinc, is a curve on its own, all right? So you see here, this signal has been reconstructed. If you merge the gray and the blue together, you have a very accurate signal at times, and by the way, with less processing power requirements. So a signal is reformed into a composition of sine waves or cardinal sine wavelets that reconstruct the signal. Model-based reconstruction finally assumes a known-signal model such as exponential, sinusoidal, and fits parameters from samples using these predefined and assumed functions, correct? It has a high accuracy when the model matches the signal. So in other words, when this model sees that the signal is close to an exponential or a sine waves, it fits a sine waves to that set of samples, all right? So it has a very high accuracy when the signal itself is very close to the model fitted, and it requires less processing power. Finally, AI-based reconstruction uses AI and machine learning to predict the shape of the signal based on a data set, based on, saved samples. And it uses, the statistical models to like infer what shape or what is the best fit to reconstruct the signal. And this adapts well complete patterns. This advantage requires training dataset. It requires dataset, and the datasets at times they might not fit to the acquired restoration signal, which is basing its learning or its prediction on the dataset. The dataset might be very far from the predicted signal, or the original signal rather. All right, so some of the DSP's applications are removing noise from audio track, because the noise has specific frequency harmonics, so we can like filter the frequencies out. Blurring or shaping or sharpening an image, filtering out unwanted frequencies in sound, high frequencies, low frequencies, the music within the music track, filtering out the voice of the singer perhaps, and many other applications. But it has a very important impact on electrical communications, but not only that, on signal and image processing, especially like in space applications. So what are the different types of signals? So at first you have continuous time signals. They are defined with a value at every instance, okay? Like an audio signal is continuous. It has values all the time, even if zeros, but still has values. Discrete time signals only defined in discrete points, meaning that every period t you have one point or one value for that signal, like the sampled audio that we've seen before. Also, deterministic versus random signals. The first represent signals that are predictable, like sine wave, like cosine wave, tangent wave, I don't know, but it is predictable. It has a form of predictability to it. And random signals have uncertain probabilistic behavior, meaning that each time they are random, they cannot be predictable. They have some probabilistic properties. So you have some pattern repeating every now and then, but it's not stable from the shape wise. Now, also you have periodic versus aperiodic signals. Periodic signals repeat over time in the same way, like the sine wave. They are rhythmic. They have a rhythmic pattern. Meanwhile, aperiodic do not. Like the impulse alone, it's not aperiodic. It's an event that happens and then disappears. Okay? Like, for instance, detecting an explosion or something crashing in the water. This is a periodic signal. It doesn't repeat itself. Meanwhile, a sine wave is periodic. Even versus odd signals. Even signals are symmetric around the y-axis. For instance, as an example, you have the sine C signal is symmetric. It has like mirror image behind the y-axis and in front of the y-axis. So it's like symmetric. It's the same, both the opposite sides. Sine wave is also the same, because sine after y-axis is the same as before sine y-axis. Odd signals. Now the odd signals, meanwhile, they are not symmetric. Actually, they are symmetric relatively to the point of origin of the axis. Finally, real versus complex signals. The former have only real values. The latter should be expressed in the real and the imaginary axis. So as an example for that, S equal R plus JC. J is the complex argument. It's on the complex plane or complex axis, and R is the real value. Types of systems. Now, the types of systems are, you have linear versus non-linear systems. Linear systems obey superposition. Non-linear do not. What is superposition? Which is additivity and homogeneity. Non-linear systems would be like yn is equal xn square. All right, so it's not additive. Let's see what additivity and homogeneity mean. additivity, so you have the response of x1n plus x2n, okay, is equal to the response of x1n plus the response of x2n. So these two functions together, when we get their response, if they are added, the response is equal to the response of each function alone added to the second one. All right, so this is to put it simply. Okay, it will be like more clear perhaps afterward. Also homogeneity, so you have the response of n is equal to a times the response or h of xn. In other words, that would be like the amplifier. So if you amplify the signal and then you get it into another circuit that will perform a modification to it, or if you insert it into the circuit that modifies it, I don't know, distorts it or does something to it, and then you multiply it by this argument, which is like an amplification argument, it would give you the same result in both ways. So either if you amplify it before it enters to the circuit or after, the output would be the same. That's to put it simply. As an example, y equal x, so ya squared plus yb squared is different than ya plus b squared. Why? Because ya squared is equal to a squared plus yb squared, if you replace x by b, that would give you b squared. Okay, a squared plus b squared, correct, is different than ya plus b squared, meaning that if you replace x with a plus b, then you square it, it would give you a different number than a squared plus b squared, ya squared plus b squared. Why? Because here you have a squared plus b squared, here you have a plus b squared gives you a2 plus b2 plus 2ab, or a squared plus b squared plus 2 times a times b. Time invariant versus time variant systems. So time invariant systems have fixed behavior over time. So yt is equal to xt minus 1. That's invariant. They have the same behavior. They don't change. But time variant do not have that characteristic. They change over time. Also, causal versus non-causal systems. Causal systems depend only on the present and past values. Non-causal systems do not. In other words, how to determine if a signal is causal or not. Let's state it in a simple way. Causal signals, if you have, let's say, y equal xn, n being instead of t, n being the time position within the axis. For n is equal to 0, that's the first symbol, n equal to 1, that would be the position of the second symbol, etc. This, for a causal signal, all the values for that signal exist for n greater than or equal to 0. So for negative n, meaning before the beginning of the timeline on the positive axis, if n is less than 0, if n is equal minus 1, minus 2 to the left of the y-axis, you should have no values for xn as a function for the system to be causal. If the system is non-causal, however, you would have values before n equals 0. In other words, it depends not only on present and past value. This means it depends on other values as well, like future. It has memory, okay? It's depending on, or like future values that are retroactive, that are received at the input and reprocessed. So to make it simple, causal signals depend only on all the values, should only have values for n greater than or equal to 0. For n less than 0, xn should be always 0, having no values for the system to be causal. That's the simplest way we can put it. Now, stable versus unstable systems. Stability implies for bounded input, yn is equal to 0.5 xn. Meaning that if you have an input, you should not have or get an infinite output. It's like me asking someone a question and he answers with a simple answer, 1 or 2 lines. That's a stable system. Meanwhile, if I ask something, then I get an article and the other person keeps on, rambling for an hour, that's an unstable system, okay? That's like, to put it in a a close example, an easy example. Also, other types of systems, lumped versus distributed systems. Lumped systems have components concentrated in one place. Meanwhile, distributed systems scatter over space. Okay, lumped systems like have a response that is concentrated in one domain, in one area. Distributed systems have values almost scattered everywhere. Memoryless versus memory systems. Memoryless systems output depend only on the current input. It doesn't depend on previous input. And finally, invertible versus non-invertible. Invertible systems allow reconstruction of the input, like we've seen with audio binary sequence. Uninvertible or non-invertible systems are not, like, we cannot restore the original signal from the output. That's the main difference. Now let's talk about elementary signals. These are the building blocks or foundation of DSP, because from these elementary signals you can form or establish more complex forms of signals by adding, multiplying, and using multiple forms or multiple types of these elementary signal blocks. Let's at first start with the impulse signal, in French impulsion de Dirac, meaning Dirac's impulse. That's delta t, that's the denotation of it. So how is this signal defined? Delta t is equal to 1 for t equal to 0, and 0 otherwise, meaning that it only exists at t is equal to 0. Of course, theoretically, it has a peak of infinity, but in electrical circuits, it has only a limited peak, a limited amplitude, which is 1 in this example. So also, what are like the different operations that can be used on delta t? We're gonna name right shifting and left shifting, which is a time shift of this function. In other words, let's say you see delta t minus 3. How to represent that? All right, so delta t minus 3, meaning that this is an impulse that exists for t minus 3. So if you imagine t minus 3 is equal to x, and for x is equal to 0, because here for t is equal to 0, delta t is equal to 1. But you don't have simple t, you have t minus 3. So you replace it by x, okay, and you solve it for t. So t minus 3 is equal to 0, then t is equal to plus 3. So this delta function exists at t is equal 1, 2, 3. This is where its value is. This is in delay of time, not in advance. Why? Because it arrived late. Meanwhile, here, delta t plus 3, which is 1 for t equal minus 3. Why? Because t plus 3 is equal to 0, then t is equal to minus 3. So it is an advancement of time. So you count minus 1, minus 2, minus 3. Why? Because it arrived much earlier than the upper one. This is what we're talking about. Unit step or echelon. So what is UT? Unit step. You have UT is a signal that is 1 when t is greater than or equal to 0. So starting from t equal to 0 and to the right, for whatever t greater than 0, this signal is equal to 1, and 0 for t less than 0, as you see here. UT is actually can be considered as the cumulative sum of the impulse signals from 0 to infinity, from 0 here all the way to the right. So sigma, in other words, UT is equal to sigma k from 0 to plus infinity delta k, meaning that it's the sum of all impulse signals from 0 to infinity. And by the way, the same applies here when it comes to delaying or shifting. We will see it later. So let's say you have UT minus 3 or UT plus 3. Okay, let's take UT minus 3. So UT minus 3, how to draw it? T minus 3 is equal to 0, so T is equal to 3, meaning that this should start at T equals 3, and you get the same shape or form, but starting, instead of 0, for t equals 0, it starts at t equal 3. Ramp signal or RT. So the ramp signal is actually equal to t for t greater than or equal to 0, correct? And 0 for t less than 0. Actually, this is by limiting it with what? With the u, meaning that you have the ramp, y equal t, that's the equation, but it's multiplied with ut. That's why it has 0 values to the left, in other words. So RT is equal to sigma k equals 0 to t, right? All over from 0 up to t of uk, meaning that you have all the t values, but starting from 0 to the right. This is what it means. Exponential signal, xt is equal to a to the power of t ut. It has a value which is at when t is greater than or equal to 0, and 0 otherwise, which is when t is less than 0. In other words, what we have here is an exponential signal that is multiplied by a unitary step signal. Why? Because it has no values below 0. All the values of this exponent are for each t greater than or equal to 0. So it is one-sided to the right. It's causal, you can say. Now, and by the way, we can get this signal by summing all the values starting from t greater than or equal to 0, but multiplied by ut. Sine wave signal, which has the form of xt equal to sine sinus omega t plus phi or cosine omega t plus phi. So it combines with exponentials in complex sinusoids. For example, e g omega t is equal to cosine omega t plus j sine omega t. It has two forms, like the exponential and the cosine, canonical form, but they are interrelated with each other. So then you have rectangular port signal. So rectangular signal or signal port, which is represented by rect. Actually, rect is equal to 1 when t is between two values. It's called also, a window function. So when t is between 0 and n, which is n here, of course 0 and n being included, it has a value of 1, or 0 otherwise, meaning that outside of that interval it has a 0 value. Port signal can be obtained by subtracting the overlap between two consecutive echelon signals. So in other words, you can obtain that by performing ut, which is starting from 0 all the way to infinity, minus ut minus n, which is a step signal that exists at t equal n. So it starts from t equal n and goes to infinity. We're going to see on the next slide how exactly it works when it overlaps these two step functions, how it is produced as a window port function. So looking at that, you have here ut, which is a step function starting at t equals 0, correct? So starting at t equals 0 goes to infinity. And then ut minus 2, for instance. So ut minus 2 starts at t equal 2, correct? Now, if you see the overlap here, after 2, both ut and ut minus 2 have values of 1. So ut minus 2 gets you 0. And before 0, they are both 0. So the subtraction only gets you a value of 1 from 0 to 2, where ut is equal to 1. Meanwhile, ut minus 2 has not started yet, is equal to 0. And it gets you this port function or window function. So port signal can be obtained by subtracting the overlap between two consecutive echelon signals. The only intersection area where the amplitude jumps to 1 is from t equals 0 to t equal 2, or n, if you will, where ut equal 1 and ut minus 2 is equal to 0. That is the area of the overlap where one of them is 1, the other is 0. So what gets you the port function over here? That's the only place where the window appears. or the port. Combined signals, xt is equal to t times u t minus 1. Let's break this signal down. At first, you have a port function, which is ut minus 1. To read that, so ut starts from 0, correct? That's a port function. ut minus 1 starts from t equal 1, because t minus 1 is equal to 0, t equal 1. So you get a port function which is like this. All right? Can you see it? This is starting from 0. That's the port. From 0 to 1. And we are multiplying that, which is a value of 1. We're multiplying it by t, which is the line, the first diagonal, we call it. So when multiply this t by 1, you get this form, this peak. Okay, this is a composite signal. So ut starts at t equals 0, ut minus 1 starts at 1. So from 0 to 1, you have the amplitude 1. When we multiply it by t, you get this line here. And of course, otherwise, t that existed outside of these boundaries of the port is annihilated by the 0 of this port function. Correct? Signal transformations or time shifting, we've already seen that. So let's see the right shift, which is xt minus t0. So this would be a signal where it exists at t equal t0, correct? Left shifts means xt plus t0, so t exists at t equal minus t0. So as an example, let's see the unit step function. So x is equal to ut minus 3. T minus 3 is equal to 0, correct? So t should be equal to plus 3. So big T is equal to t minus 3. For t greater than or equal to 0, you have ut equal 1. What is that value of big T? This is t minus 3. So t minus 3 is equal to 0, t equals 3, and you get this signal, unit step echelon, starting at t equals 3. Level 1 all the way to the right. Correct? I hope it's clear. Now, reverse signal or x minus t. So what does it mean, x minus t? Let's say xn is equal to 0, 1, 2, 3, 4, etc. X minus t should be equal, is equal to 0, 1, because for each n, x, the new x is equal to the x of minus n. In other words, you have for n equal to 1, you get x of minus 1. All right? So for each value, you have the reverse of it. This is what we're saying here. So let's say for n equal to x, the new x is equal to, it is the x of minus 2, correct? Minus 2, which is here. So I hope it's clear. So xt equal t, x minus t equal to minus t, which is the reverse function. Okay, this is what we're referring by as reverse. I hope it is clear. Okay, so we're reversing the time. When you reverse the time, like 0, 1, 2, 3, we're reversing them. You get the mirrored image relatively to the y-axis, vertical axis here, which is xt, not y in this case. Time scaling. So let's say a signal is xat, that's the scaled signal. Now, when a, absolute value of a, is greater than 1, we are doing time compression. When absolute value of a is less than 1, we are doing time expansion. So let's explore that in a more descriptive example. So you have xn is equal 1, 2, 3 at n equal 0, 1, 2. The signal is actually the blue one. All right? You have these values here, the blue, for the first signal, which is xn. What do you mean by x2n? So 2 times 0, let's display, x2n would be the signal in red, x2n. For n equals 0, and 2 times 0 won't make any difference, so the value of x2n would be the same as the value of xn, which is the value at 0. It happens here to be 1. You see the red on top of the blue, red being the values of the new function of x2n. Okay, now for n equal 1, x to n is equal to 2, correct? So, meaning here, the value of the red signal at n equal 1, okay, since you have 2n, so this value of the red signal is actually the value of the blue signal xn at what? At n equal 2, correct? So at n equal 2, you have the value is 2, okay, correct? So then the value of x02n is 2. You see what's happening? So another example. For n equal to 3, correct? X to n is equal to x6. Okay, so here we are standing at, actually, yeah, what position are we at? Okay, 0, 1, 2, 3. That's the position we have. Okay, so x to n is equal to, x to n is 2 times 3, which is x6 over here, correct? x6, now x6 is not defined. We don't have a value for x6. Okay, let's try this one. Let's go back to, let's say, yeah, -1, okay? So for n is equal to -1, the new x is x2n, okay? So at -1, the red signal is equal to x minus 2, which is -1 times 2. What is x minus 2? X minus 2, the blue one, is this value. So the red signal at -1 is equal to x minus 1 times 2, which is x minus 2, correct? So this value is transmuted to this value. I hope it is clear. So giving also another example, let's say you have for x minus, for n is equal to -3, correct? For n equal -3. n equal -3, x to n is x minus 6, okay? So for n equal -3 at this position, x to n is x of -6, the original x, the original blue signal at -6. What is that value here at -6? It's 0. So you place it here. Now it happens to be the same. Also, another review. For n equal -2, meaning for this position, okay, x to n is x2 by -2, which is x minus 4. Okay, so at t minus 2, okay, the value is that of -4, correct? What is x minus 4? This is 1, correct? And you see the red, we place the red, which is +1. Why? Because x to n for n minus 2 is actually x2 times -2, which is -4. So this value is placed here for the red signal. Okay, I hope it is clear. Again, another example for n equal -1. Again, for -1, you have x minus 1, of course, it is, 1. Okay, but what about for xn? But what about x to n? For n equal -1, x to n is 2 times -1, which is x minus 2. So the red value here is that of the blue value at position -2, which is 2. So we place this value here at this position. Okay? I hope it became clearer at this point. Now, and again, by the way, if, going back to reference to the previous slide, why are we talking about time compression? Because you're multiplying the time by a factor, so it's compressing the values. Meanwhile, when you have a less than 1, you have values, like you are distributing the time over a larger span, okay? You are taking fraction of the time, so you get a time expansion. Okay, now amplitude scaling, yn is equal a times xn. Okay, for a greater than 0, you get an amplifier. For a less than 0, you get a choker or an inhibitor of the signal, okay? It like decreases the signal. So let's represent it here. You have xn is equal 1, 2, 3, 4. These are the sequential values, by the way, for xn, okay? These are not the indices, these are the values. So xn is in the blue, you have 1, okay, 1, 2, 3, 4, okay, they're not quite well represented over here. Okay, 2xn, Actually, yeah, we have a different signal down below. Forget about it. Okay, 2xn is 2 times xn, meaning 2 times 1, 2, 2 times 2, 4, 2 times 3, 6, 2 times 4, 8. Okay, that's an amplifier. Now forget about this. Let's see here. This is not a representation of this signal on the above level. Okay, this is a completely different signal. But let's see as a demonstration. So you have the blue signal is the original one. So when you have the blue signal is at 0, 2 times 0 would give you, of course, 0. But when it is at 1, 2 times 1 gives you 2. Okay, that's the red signal. Again, 2 times 0, 0. But here you have 2 for the blue signal, the original one. The amplified one is 2 times 2 would get you 4. You see? So this is a more powerful signal. Here 1, 2 times 1 get you 2. 2 times 1 get you 2. The red is the amplified signal. 2 times 0, of course, 0. Now, 2 times 2, 4. Okay? We're amplifying like the signal values. Okay? We're not actually performing anything, any scaling to the time like the previous slide. We are scaling only the amplitude. And when you have A less than 0, what you get is a choked signal and like a decreased signal instead of an amplified signal. That's the main difference. Again, this graph down below has nothing to do with this function. Signal addition, subtraction. So you have x1n 0, 1, 2, x2n 2, 3, 0. Yn is x1n plus x2n, which is 0 plus 2, element by element. 1 plus 3 and 2 plus 0. You get a vector of the same size, which is 2, 4, 2. 2, the first two being 0 plus 2, then 1 plus 3 gives you 4, 2 plus 0 gives you 2. Now, that's the addition. Subtraction, that's another operation with signals. Okay, so yn is equal x1n minus x2n, which gives you 0 minus 2 minus 2, 1 minus 3 minus 2, and 2 minus 0 plus 2. Okay, so let's say you have x1n is the signal in blue, x2n is the signal in green. Okay, yn is the signal in red. So here you have 0 plus 2 gives you 2, 1 plus 3 gives you 4. You see, 1 plus 3 gives you 4. Okay, and 0 plus 2 gives you 2. So you see the red signal is actually the result of the addition of the two signals x2n, having, by the way, regardless, I don't think they have the same values as here. Okay, yeah. Okay, 0, 1, 2, that's the addition example here. And 2, 3, 0, meaning you have 2, 3, 0. Okay, starting, by the way, from indices 0, 1, 2, etc. That's a causal signal. So for each value, like here, the first value corresponds to the first index, to the first n. Second value, which is 1, to the second index. Third value, which is 2, to the third index, 0, 1, 2. Okay, then x2n is starting from 0. That's 2 at 0. Then 3, which is the second index, 0, the third index. Okay, so when adding them together, you get this red signal. Combined signals. So the equation of a signal is the sum of the elementary signals from which it is made of. All right, so here we get this complex signal. We need to break it down. Actually, we need to get its equation based on, or through breaking down all the elementary signals that this compounded signal is made of, starting from the first one. Okay, so what do we notice here? This is actually a ramp. How do we get the equation of this line? Let's start with that. Okay, the equation of this line, so it is bounded by 2 points. The coordinates of these 2 points are respectively -6, 1, correct? That's the first point. And the second point, which is here to the right, down below, -5, 0, correct? Because on the y-axis or xt axis, that's 0. But on the t-axis, which is the x-axis usually, it is -5. So, -6, 1 and -5, 0. The equation of a line is x equal at plus b. We replace the 2 points, correct? We replace x and or y-axis and x-axis, if you will, but here the y-axis is x, the x-axis is actually t. So I hope you're not confounded with that. So we replace x and t with the coordinates here. You get 1, correct, is equal to -6, which is, at the t-axis, a plus b. Then the second point, you fill it in. 0, which is at the x, is equal to a times t, t being -5, correct, plus b. You mix them together, what you get is 1 is equal to -a, okay, by replacement, of course, and b is equal to 5a. Why? Because when you move b to this position to the left of the equation, you get -b equal -5a, so b equal 5a, and then you replace that in the upper equation. -6a plus 5a gives you 1, so -a is equal to 1 and b equal -5, so xt is equal, that's the equation, -t -5, correct? Why? Because we're replacing a and b in this equation. So xt is equal -t -5, but it is windowed. You have a port function that limits this line equation between -6 and -5. So -t -5 times unitary function, okay, from -6, which is t plus 6, you see? Because this is where t equal -6, so t plus 6 equals 0, correct? So ut plus 6 minus ut plus 5. Why? Because the second port existed at t is equal -5, so t plus 5 should be 0, okay? That's the first equation. Second equation, what you have is a line between -5 and -3. So we need a port function from -5 to -3, and we need to get this line equation. Okay, let's start from the easy part. What is the port between -5 and -3? That would be u t plus 5, because t plus 5 equals 0, t equal -5, minus ut plus 3, meaning, ut plus 3, so t plus 3 equals 0, t equal -3. So ut plus 5 minus ut plus 3, that's the window, times this line function that we need to figure out. What are the 2 points that connect this line? These are, the first point, -5, 1, correct, xy, -5, 1, and the second one is -3, -1, correct? So we replace the 2 points together in x equal at plus b, and you get a and b. We solve the equation and we get -t -4 times the port function. Okay, this is how you get this line equation. Now, next, you have a simpler function. This is simply from -3 and -2, a port function between -3 and -2, having amplitude 1. As simple as that. So this is u t plus 3 minus u t plus 2. Why? Because the first exists at t plus 3 equals 0, so t equal -3, and the second also for t equal -2. So u t plus 3 minus u t plus 2. Next to it, you have another port function spanning from -2 to -1, except it has an amplitude of 2. So what we need to do here is to multiply by 2 this port function, which is ut plus 2 minus ut plus 1. Now, between -1 and 0, you have this function. So, at first, again, let's start with the simplest part of this, trunk, or this fraction of the signal, which is the port signal, standing from -1 to 0, which is from t plus 1, ut plus 1, to ut. So, ut plus 1 minus ut gives you this port, this window. All right, now we multiply it by the function, which is the line. How to get the equation of this line function, of this ramp, so to speak? You have 2 points, the first point being -1, 2, correct? And the second being 0, 3. So 2 equal -a plus b, 3 equal b, correct? we replace them by this equation, you get 3 equal b and a equal 1, so it is t plus 3. Okay, so for for t equals 0, the function is equal to 3. That's correct. For t equal minus 1, the function is equal to 3 minus 1, which is 2. So that's the correct function. So in case we've done any mistake, you can confirm that by matching the points. If you see if the points match with the function. So you multiply t plus 3 times ut plus 1 minus ut. It gives you this ramp from t minus 1, from t equal minus 1 to t0. After that, you have this port function and the delta function right next to it. The port function is from ut to ut minus 1. Why? Because ut, you get the echelon here, minus ut minus 1. So for t equal 1, you get the other delimiter of the port, correct? And the intersection is this window over here, or this port. Plus, you have an impulse, correct? And this impulse, by the way, is actually multiplied by 2. So here we have a mistake. This impulse needs to be multiplied by 2, correct? Let's actually erase that. Why? Now, why is it multiplied by 2? Because this impulse has an amplitude of 2. Okay, so it is an impulse. By the way, it exists at t minus 1, meaning that for t equal 1, we have this impulse, and it has a height of 2, so we should have multiplied it by 2 over here. For this function, now we can do it in a simplified way instead of going through the process of finding 2 points, because here is the thing. If you notice something about this function, actually it is 2 ramps superposed to each other, against each other, or back to back. Okay, let's start with the first one. So of course you can do it using the first way that we've done it, which is finding the 2 points that make up the line, and of course we multiplied by the port function. However, of course, the port function thing will not change, but what I'm trying to say is trying to find a way to get this function without finding the points connecting the two, the line of this function. Okay, the same thing for the one right after it. So let's start with this one. If you notice something, this is actually the ramp function going from 0 to 1, except it is slidden 2 steps to the right. So it is time shifted 2 to the right. Okay, so here's the function of t. It is in time delay, shifted to the right. So this is t minus 2. And if you replace it by the points, you'll find that this is the exact equation of this function over here, multiplied by the port, which is between 2 and 3, or ut minus 2 minus ut minus 3. Why? Because for t equal 2 and t equal 3, this is the port function. Great. So that's the 8th function over here. Now let's get the other one, which is right next to it. x9t. All right, now this is the ramp function, but it is inverted. So if you imagine that this is the function, okay, it is inverted. So that's x minus t, but shifted for actually this, it is shifted 4 to the right. So x minus t plus 4, okay, because here we have minus, that's why. Okay, minus t minus minus 4 plus 4. So this is the function, and it is between 3 and 4. So ut minus 3 minus ut minus 4, you get this function. So x8 plus x9 would give you these two line functions. Linear time invariant system LTI properties. So what are the different properties of this system, which is linear time invariant system? First is the convolution. That's the first property. So what is the convolution? The convolution is a mathematical operation describing how an input signal xn is processed by an LTI system. In other words, let's say you have a signal at the input of a system, which is xn. Okay, so the resulting signal, which is the signal at the output of the system, is xn. The input signal convoluted, not simply multiplied by, but convoluted by hn, which is the response of the system. So hn would be like, let's say for an amplifier, to make it simple, that would be a product of, an integer value, which is the amplification factor, or it can be a float, but let's say for simplicity, that would be number 3 multiplied by the signal. So the signal is being amplified 3 times, all right? That would be the response of the system for any input signal. So any input signal is multiplied by 3, amplifying its value, all right? So the convoluted function or the convoluted vector is gotten by this equation, which is sigma k going from minus infinity to plus infinity for supposedly an infinite signal, xk, which is the signal, times hn minus k. It does mean that that's the source signal multiplied by the response, which is shifted by k, and each time we need to add all of these versions of the signal. Okay, so for k equals 0, k equal 1, etc., we multiply, then we add. All right, now it won't be obvious, it won't be evident here because it's a little bit complex mathematically, but we will break it down and simplify it so it would be understandable. So how to compute? You flip one signal, usually hk, multiply, shift meaning shift to the right. You multiply and sum over all the time as long as you're shifting. So let's say you have xn is 1 1, hn 1 1. Okay, yn is xn convoluted by hn, which is what? 1. It gives you 1 3 2. How did we get that? We're gonna see it in the next example. All right, so or basically, if I want to simplify it a little bit right now, you place 1 1, the hn, right below 1 2, but shift it to the left. Okay, so 1 1, 1 times 0, 1 times 1, 2 times 0. You fill in zeros where there is no vector. Okay, and you sum it, you get 1. That would be the first value. Then you shift it to the right. You have right now 1 2, and right below it 1 1. So that's 1 times 1 plus 2 times 1, that's 3. That would be the second value, etc. But it will be simpler in the next example. So this is how we do the convolution. Let's start with this example. So you have you have one signal, which is xn equal 1 2 3. 1 2 3 are the values, not the indices. All right, we need to make the difference. So 1 2 3 are the actual values. In other words, for n equals 0, which is the first value, right at the the vertical axis, you have 1. Then right next to it, you have amplitude of 2, you have amplitude of 3 right next to it. And hn is the response of the system, which is 1 0 1. At first, what would be the dimensions of the resulting vector, which is the convoluted vector? That's the result of the convolution product of xn convoluted by hn. The dimensions of this convoluted vector is given this way. All right, we can calculate it using this method. First, you get the dimension of xn, which is, you have 3 elements, so it is, correct, 3 items, plus the dimension of hn, which is also here in this example 3 items, minus 1. So you have 3 plus 3, 6, minus 1, correct? So the dimension of yn is 5 items. It will have 5 items in it. Okay, how do we get these items? We start by the first item. At first, you need to place 1 2 3, and you shift hn all the way to the left until you have an overlap, if you will, between the last element of hn and the first element of xn. You see here, you have 1 2 3 and 1 0 1. We start by, shifting it all the way to the left, the hn, in a way that the last element here is right below the first element of xn. The last element of hn is right below the first element of xn. Okay, and you fill the void by zeros. So what is the first item? That's 0 times 1 plus 0 times 0 plus 1 times 1 plus 2 times 0 plus 3 times 0. All of these are 0 except the first, the third, which is 1. So you get 1. That is the first item. Now, you shift this quantity here to the right. Okay? So you see 101 is shifted to the right. So now you restart the calculations. You have 0 times 1 plus 1 times 0 plus 2 times 1 plus 3 times 0, which is 2. That's the second item of the vector, which is here. We placed it here, 2. Okay, then we shifted again to the right. We shift hn to the right. Now they happen to be right on top of each other at full overlap, if you will. And we redo the calculation. It is 1 times 1 plus 2 times 0 plus 3 times 1, which is 1 plus 3 equal 4, because here it is eliminated. That's 0. Great. The fourth item, now we shifted also to the right. Every time we are shifting hn one element to the right. So 1, 2, 3 and 1, 0, 1. You have 0 here. Okay, and let's redo the calculation. 1 times 0 plus 2 times 1 plus 3 times 0. Okay, so we get only 2 here. The other items, the other multiplications are 0. Great, that's 2. And the fifth item, finally, you shift 101 all the way to the right until the last element of xn overlaps with the first one of hn. Okay, and 1 times 0, 2 times 0 plus 3 times 1 plus times 0 plus 0 times 1, okay, is equal to 3. That's the last item. Now, why there's no need anymore to shift it to the right again? Because if you shift it once again to the right for the hn, there are no longer any overlapping elements to multiply, because they would give you 0, which are zeros right to yn and left to the yn, left to these elements. But if you notice it here, the number of elements or the dimension or size of yn is 5, which is 1, 2, 4, 2, 3. Count them, you get 5 elements, just as we've deduced here. And this is the product of evolution. Actually, you can take a picture of that and, you know, try an example for yourself. And it's quite straightforward and easy. It's not actually that difficult. I hope it made sense. So that's the convolution product. Now, because of the relationship between xn and hn, knowing the impulse response of the system, we should know hn. Okay, so knowing this impulse response of the system can make us understand the entire system and how it behaves. So that's why it's important to know hn, okay, so that we can predict how the system will treat the input xn and what would be the resulting convolutional product, the resulting signal, if you will, at the output of the system. Linear time invariant properties, causality. Okay, now we're going to talk about causality of a system. So what does it mean, or what do we mean by causality? Causality means that the output depends only on present or past inputs. So technically speaking, for a signal, hn exists or has actual values for n greater than or equal to 0. So hn has values for n greater than or equal to 0. Meanwhile, whenever n is less than 0, all the values for xn, okay, all the values would be null. So the system does not have any values below n equals 0 or for n less than 0. All right, so hn is equal to 0, or the response of the system here, to be clear, the response of the system is equal to 0 for n less than 0. Okay, so xn equals 3, 4, 5, 6 for n equals 0, 1, 2, 3. However, it is 0 whenever n is, or for whatever value of n that is less than 0. That's causality. Stability. So what do we mean by stability? Stability meaning that the limit when n goes to infinity for a system it doesn't go to infinity, so it's not open-ended. It leads us to a value that is fixed and finite. So a bounded input has to lead to finite bounded output, and hence the response of the system should not be infinity, converging instead to a fixed final value. So at first, stability is given by this relationship, so sigma minus infinity to plus infinity of Hn, which is the response of the system, should be less than infinity. Actually, not equal to infinity, but less than for stable systems. But that's the relationship. So as an example, you have Hn equal 1 over 2 to the power of n un. Now, okay, this is a geometric sequence, all right? So 1 over 2 to the power of n. By the way, un always starts from 0 and to infinity, but it does not have any values less than 0. So anything multiplied by un, it gives us a causal system. Why? Because for n less than 0, all the values are 0. Why? Because you have the echelon signal here multiplying this function, whatever it is. You have the unit step function that forces all values to be right at the right of the y-axis, which is for all positive n values. Otherwise, for the values or for the indices that are less than 0, we have no values. That's why it is causal. Whatever is multiplied by un would give you a causal system. Now, for stability, let's check the limit for 1 over 2 to the power n. That's a geometric sequence that gives you 1 over 1 plus 1 over 2 equal to, so it is less than infinity, then it's a stable system. Okay? Now, however, for Hn equal n power un, so the limit when n goes to infinity is actually infinity. So it's not stable. It doesn't give you a finite bounded output, okay? It goes forever to infinity. So it's not a stable system. This example is not. The first one is why? Because when n grows, the system tends to the value of 2, which is a bounded value less than infinity. The transform. Now, this type of transform actually converts the signal from the time domain into a complex function, not a frequency domain per se. No, it is converting the signal into a complex function that has, you know, R, like real and imaginary values. Plus, it gives us an overall idea on how the system behaves, what are the peak values of the frequencies passing through the system, and what are the system or the frequencies that are attenuating. In other words, you have the concept of poles and zeros, and we will get that later. We will understand what it is referring to. So for poles are where the signal goes to infinity, okay, for the frequencies for which the signal or the system goes to infinity, meaning that it is peaking or amplifying these frequencies. It is at best for these frequencies. And zeros are the frequencies or the frequency values for which the system is zero, attenuated to zero, meaning that these frequencies are cancelled out or heavily attenuated. Unlike the Fourier transform, for which you have a signal in the time domain, it switches in the frequency domain. So this representation pertains to Fourier transform, not Z transform. Okay, so for Z transform, it actually converts the system into a complex value, a complex representation. What is the Z transform? So for xz equal sigma minus infinity to plus infinity xn, okay, xz. So Z transform is equal to the sum from minus infinity to plus infinity xn times z to the power of minus n. All right? So these are the different representations of the Z transform. So at first, we're talking about the basic properties of Z trans. So you have linearity, meaning that axn plus b yn is actually, or it can lead us to axz plus byz. Okay, so it's linear. is the sum of the transform, so to speak. Time shifting, so when the time is shifted for xn, that will also affect xz, which is the z transform for xn. Frequency scaling, so xn gives us xz over a. That's the frequency scaling, so we need to understand these operations. Time reversal, in other words, x minus n is x 1 over z, which is the inverse of z, or xz minus 1. 1 over z gives us z to the power of minus 1. Multiplication by xn gives us, okay, minus z d over dz xz. So we always look up this chart to understand how to perform the z transform. You don't need to memorize them. Just getting an idea to understand how they work. Another page here, multiplication, cosine. By the way, cosine xn would give you, okay, 1 over 2 x e j omega z plus x e minus j omega z. Why? Because if you can recall or remember, we know that cosine theta is equal or can be transformed into an exponential form, which is theta minus e or plus e minus theta over 2. Okay, now for the sine is transformed into the exponential dimension, if you will, or it can be reformed into an exponent by e theta minus e to the power minus theta over 2j. But of course here it's a multiplication with xn, so to j, yeah, actually he switched the place of j. When you multiply j by another j, it gives you j squared, which is minus 1. You multiply the and the numerator, so you get something like that. Okay, I'm not gonna get into the detail on how he regrouped this, okay, but you get the point. So accumulation, meaning sigma k 0 to n xk gives you z over z minus 1 xz, okay, etc. And the convolution also gives you a product of hz. So some of the main transforms, okay, and the region of convergence. Region of convergence means the regions where this system or the values exist. They are not infinity. This is what convergence means. So let's start with delta n. Delta n, the transform for delta n is 1, which is, by the way, the same as value of the impulse. Region of convergence for all values of z, because no matter what z is, okay, it will converge. It is a constant value, no matter what z is. All right, now for un, which is the step, the transform of un is 1 over 1 minus z to the power minus 1. Now, what is the region of convergence? Here we need to solve it for z, okay, but which is, by the way, in other words, so it converges while actually, yeah, or it goes to infinity when z minus 1 is equal to minus 1, correct? You solve the denominator for 0, so z minus 1 is equal to 1, z is equal 1 over 1, which is 1. Okay, so for z, absolute value of z is greater than 1, it converges. Why? Because if it's less than 1, actually, yeah, for 1 minus 1 equals 0, it goes to infinity, so you cannot have that. Okay, so z should be greater than 1 here. Z less than 1 for minus u minus n minus 1. Okay, so you look up this table in order to resolve any problem that you get. Okay, here are the main functions. Cosine 1 minus cosine. Okay, so in order, when you get a problem, you need to transform it using this chart here, this reference. Okay, so for sine omega 0 n un, you can transform it immediately to this form over here. Convergence is z greater than 1. So restoring, how to restore xn from xz, meaning from the transformed form to the original signal, to the original form. So one of the methods is long division when xz is rational, dividing numerator by denominator and express as a power series and z minus 1. Partial fraction expansion, so breaking xz into simpler terms, Okay, restore the parts using their known inverse pairs for these simpler terms. And finally, residue method, which is contour integration. So xn is equal 1 over 2 pi j integral xz times z to the power n minus 1 dz. Okay, this is how you restore. So let's say, for instance, you have a function which is a to the power n un. Okay, so it has a transform 1 over 1 minus a z minus 1. A is an integer or a value, actually. A could be an integer or a float, okay, but it's a positive value. So z should be greater than a in absolute values for the convergence, for the region of convergence. So xz is equal sigma 0 to plus infinity a n z to the power n is equal to divided by a z to the power minus 1. ROC is z, absolute value greater than a. Okay, so that's the transform. For un, you have 1 over 1 minus a z minus 1. That's the transform. Okay, and the convergence is z greater than a in absolute values. Okay, so we got that from the table. Now, second example, xn is equal delta n plus 2 times delta n minus 1, which is shifted to the right, as you notice. An impulse, which is, by the way, it is twice the amplitude. This impulse is shifted to the right, but it also has a peak of 2, plus delta n minus 2, which is also shifted 2 steps to the right instead of 1. Okay, so what would be the transform? Delta n, if you consult the table for delta n, you know, the transform is 1. Okay, then plus, here it is shifted. You see, delta n minus n gives us the transform z to the power minus m. Okay, so which is what? Delta n minus 1. Okay, so here the shift is plus 1, correct? That's m, as m is 1. So 1 plus 2 times z to the power minus 1. Here m is equal to 2, because n minus 2, n minus m is equal to 2, so plus z to the power minus 2, correct? That's the transform for this sum of impulses or delta functions. And of course here, you know, through the laws of linearity corresponding to z function, you can 2xn is equal to 2xz, correct? That's the linearity. So delta n was multiplied by 2, you multiply also the transform by 2. It works this way. Now, about the properties of the system. The system is causal because xn is equal to 0 for whatever n less than 0, because all the values are to the right of the y-axis, if you will, to the vertical axis, or all values exist for n values that are positive, for n equal 1, for n equal 2, for n equal 0. So it's causal. For n less than 0, we have 0 values. There are no values. And the ROC is what? Is z different to 0. That's the ROC. Okay, the region of convergence, z is different to 0. Second example, xn is equal to 0.8 to the power n times un. So we have a value, that's the form of it, a to the power of n times un, which is the unit step function or echelon, plus 2 times 0.5 to the power n minus 2, that's shifted, times un minus 2. Another step function, but it is shifted 2 steps to the right, and you have a to the power n minus 2. So let's check the transform at first of the first element, which is x1n, if you will. The first item, the first part of this equation. So let's look to the chart, correct? To the table. So you have a to the power n un gives you a transform of 1 divided by 1 minus a times z to the power minus 1. A here is 0.8, so 1 divided by 1 minus 0.8 times z minus 1, as simple as that. And the region of convergence is z greater than a, so z greater than 0.8, correct? Now, For the second part, which is 2 times 0.5 n minus 2 un minus 2, correct? Here, this is a shifted sequence by 2 to the right, correct? Now, z2n, which is the transform of this part, of this chunk over here, is equal to, now 2 you multiply with it because of the law of, you know, additivity and linearity, because it's a linear function. You can multiply with it because 2un is 2 or 2xn is equal to 2xz, okay? So it's linear, it won't change anything. 2 times, all right. Now you have 0.5 times n minus 2. Here, this is a shift of minus 2, correct? So you have z minus 2 to the power minus 2, okay? Times what? 1 divided by 1 minus 0.5 z minus 1. So actually, to break it down a little bit, to simplify it, this is the same thing as the first one. So imagine, forget about the minus 2 over here, okay? This is actually the function, and forget about the 2, number 2 to the left, okay? It won't matter. This is the same as saying it is 0.5 to the power of n times un, okay? But it is shifted 2 steps to the right. But let's start with the first part of my expression. So it's 0.5 to the power of n un. What would be the transform for that? That would be, just like the one before it, 1 divided by 1 minus 0.5 times z to the power of minus 1. Great. Now, the second step, okay, noticing that it is shifted 2 steps to the right. How do you shift it? How do you transform the shift, if you will? Simply by multiplying by z to the power minus 2. As simple as that. And finally, you multiply by this 2 over here, which is simply a number, a multiplying number, okay? But it linearly multiplies also the transform, so equal to the power z minus 2 times 1 divided by 1 minus 0.5 z minus 1. Finally, so you have x or z2n and here z1n, you add them together and you get the final number, the final transform. So this is the final transform. You had z1n, z2n, so xz equals z1 x1z, okay, sorry, x1z plus x2z, which is this part. You add them together. This is the entire number. Of course, you expand it if you want to see, to check what we call the poles and zeros, or like the values at the denominator and the numerator. We're going to talk about that in a moment, actually. What are the poles and zeros of an equation? Now, at first, this system is causal. Why? Because xn is equal 0 to for whatever n which is less than 0. Why? Because when you have a step function, okay, starting from un, whatever is behind n and whatever is behind 2, by the way, which is n minus 2, meaning at 2, okay? So for n less than 0, you have no values because un starts from n greater than or equal to 0. So it's a causal system because there are no values before or for n less than 0. Okay? Now, let's also measure another thing. So you have the ROC, or region of convergence, x1z has ROC z greater than 0.8, correct? Based on the chart we've seen before. x2z has ROC, which is z greater than 0.5. So ROC, or the region of convergence for a causal system, by the way, because it is causal in such case. The region of convergence is the region which is, okay, outside the outermost, what? Z value here, which is outermost pole, by the way. Okay, z 0.8, that's a pole. We're going to see what a pole mean. We haven't yet started to calculate them. So here's some definitions. So this is, by the way, the answer. Now, causality again. The system is causal. Both the left and the right parts of the equation start from 0 and are right-sided. Okay. Stability, yes, which is the left part of the equation and the right part, if you go back to the previous page, okay, you have un, correct? So it is causal. Why? Because it always starts from n equals 0. There are no values for n less than 0 for this equation. And yes, for stability, the system is stable. It has a finite value. If z minus 1 goes to infinity, this annihilates the entire equation. xz becomes 0, okay? For z minus 1 going to infinity, okay, the system becomes 0, so it's finite, correct? Actually, we usually solve it for not z to the power minus 1, okay? It's the same almost. So let's talk about poles and zeros, which are what we call the residues. Okay, so the form of a z transform would be this form right here, which is a numerator value divided by a denominator value. Both are complex numbers. But what is the concept of zeros and poles? Zeros, so you have pz is the numerator, qz is the denominator. Of course, pz and qz are actual complex functions. Okay, so zeros are the values for which the numerator is annulled. So for which values pz becomes 0, that's what we call the zeros. So let's say pz is equal to z plus 3. pz is equal to 0 when z equal minus 3. So z equal minus 3 is a 0, is what we call the 0, okay? And is represented on the complex circle, the unitary circle, by what? By a rounded circle, okay? Now, a rounded dot, if you will. Technically, for a filter or a system, this represents where the frequencies in a filter are cancelled out, where you have a hard or a drastic attenuation of the signal. This is what we define by a 0. Meanwhile, what are poles? Poles, however, are the values that render the denominator 0, meaning that for which values qz becomes 0, these are the poles. Actually, if qz becomes 0, then hz goes to infinity. So let's say qz is equal to z plus 2. So for z equal minus 2, qz is equal to 0, and hz goes to infinity. These are the peaks of the system. These are the frequencies for which the system has a high peak, a high resonance, or what? A high performance. So these are the frequencies that are the most accentuated, for which this filter or this system operates the most. It has the highest amplitude or power for these specific frequencies. So z equal minus 2 is the pole. Technically speaking, it represents the peaks or resonance points of the filter, because hz is either a circuit, a filter, whatever you name it. It's a system, okay, that is behaving in a certain, in a specific way when it gets an input on the inside of it. All right, so let's give you another example. So hz is equal to pz divided by qz equal 1 minus z to the power minus 1 divided by minus 2 plus z to the power minus 1 times 0.5 plus z minus 1. Okay, let's calculate the zeros at first. Zeros are, again, the values for which pz, or the numerator, becomes 0. So 1 minus z to the power minus 1 is equal to 0. Now, z, which is the inverse of z, because z minus 1 is 1 over z, correct? We need z, not z minus 1. So z is equal to 1 over 1, because z to the power minus 1 is equal to 1. Z is equal 1 over 1. 1 divided by 1, which is the inverse, is equal to 1. This is the 0, okay? How do we represent it? So it is on the unitary axis, exactly on the circle, which is, this is the one, okay? On the real axis. Now, for the poles, you have two components multiplied against each other. So if either one of them is 0, okay, that would give you the entire denominator to be 0. So we start by the first one, which is minus 2 plus z to the power minus 1 is equal to 0. So z minus 1 is equal to 2. Z equal, which is the inverse, 1 over 2 or 0.5. That's the first pole. The first pole is represented, that's here, z equals 0.5, mid distance from 0 to the unitary circle. Now, for the second argument, which is 0.5 plus z to the power minus 1, so z to the power minus 1 is minus 0.5, z is equal 1 divided by minus 0.5, which is what? Minus 2. Okay, so it's either here or here. Actually, yeah, one of the two ways. It should be minus 2 over here. Okay, it's the same, however. It's still the same. Now, if the system is, here we have three cases if we don't know the system, what the system is about. If the system is causal, the region of convergence is outside the outermost pole. What is the outermost pole? That's 2 or minus 2 because it's symmetric for z. Okay, so this is minus 2, that's the pole. The region outside of this pole is the region of convergence for z greater than 2 if the system is causal, correct? Now, second case, if the system is anti-causal, then the region of convergence is the region to the innermost of, that's inside the innermost pole, which is the exact opposite of the causal system. What is the innermost pole? The innermost pole is 1 over 2 or 0.5. The pole that is the closest to the origin. So the circle which is going through that pole, that would be the region inside of which you have the convergence or ROC. For the third case, you have a double-sided system. What do we mean by double-sided? This is when the region of convergence, so it's not causal, neither anti-causal, you have the convergence is between the two poles. That's the ring formed by the boundaries of the innermost pole and the outermost pole. Let's get, or let's, do another example. Hz is equal Pz over Qz. That's a more simplistic example, which is equal to 1 plus z to the power minus 1 divided by 1 minus 0.5 z minus 1. Let's find the zeros at first. So 1 plus z to the power minus 1 is equal to 0. That's Pz equal to 0, which is finding the values that annihilate the numerator. So z is equal to minus 1, correct? Why? Because z minus 1 is equal to minus 1, then z, which is the inverse, is equal to 1 divided by minus 1 or minus 1, the same thing. Now that's the 0, okay? So for z equal minus 1, that's the first 0. For the poles, 1 minus, which is the value that annihilates the denominator. So 1 minus 0.5, z to the power minus 1 is equal to 0. Z minus 1 is equal to 1 divided by 0.5. So z is equal to 0.5. To 0.5, why? Because it's the inverse. All right, so let's locate it. That's 0.5. That's the pole. We have no other pole over here. Determine ROC given the system is causal. So suggesting that the system is causal, simply the ROC is the region outside of the outermost pole, which is the only pole we have here, or 0.5. That's the ROC region outside of the radius 0.5 circle. Now, is the system stable? And by the way, z greater than 0.5, that's the entire region here. Is the system stable? Yes, it's stable because the unit circle lies within ROC, within the region of convergence. Let's talk about Fourier transform. So, according to Joseph Fourier, every random signal can be transformed into a sum of sine waves or sinusoidal signals, which comprise sine and cosine waves. It's the same thing. Also, a time domain sinusoidal signal can be transformed from the time domain into the frequency domain. In other words, Fourier breaks down a signal into a sum or integral of sine and cosine waves of different frequencies, phases, and amplitudes. What's the point of having Fourier transform? So Fourier transform helps analyzing frequency harmonics of a signal, designing filters, audio compression, and restoration. Actually, there's a great benefit in transforming a signal from the time domain to the frequency domain, because hence we can represent a sine waves or a sine wave into its own frequency plus the amplitude, instead of representing it in the time domain, which takes much more space. So Z transform is for general system analysis, like finding poles and zeros, finding where the frequencies are cancelled or which frequencies are at peak and resonant within the system. But for Fourier transform is for frequency analysis. For continuous time signal xt, so you have xf is equal to, that's the transform by the way, xf is equal to integral plus infinity xt times e to the power minus j to pft dt. This is how we transform from the time domain to the frequency domain. For discrete time signals xn, you have xegw is equal to sigma minus infinity to plus infinity, because we're talking about the discrete time signals, xn instead of xt times e to the power minus j omega n. So as an example, you have cosine 2 pi f0t, okay? The transform of cosine 2 pi f0t is 1/2 delta f minus f0 plus f plus f0. So you have two impulse signals, okay? One shifted to the right, one shifted to the left, divided by 2, representing what? The cosine 2 pi f0t, the cosine signal, or cosine omega 0t. Now this looks familiar a little bit, no? Because cosine omega t, that's equal to e omega plus e to the power minus omega, correct? Divided by 2. So this is what we're having here, because I think, yeah, the transform of e j omega is a delta function. These are the different transformations. Of course, we're not compelled, or we actually cannot memorize all the transforms, but you need to have the table with you in order to resolve a Fourier transform problem, just as you need the Laplace transformations with you when you need to do that as well. So the transform for delta t is 1, delta t minus t0 is e minus j 2p ft 0, correct? E minus j omega t0, etc. Okay, yeah, here's the example that we've seen moments ago, because as we've mentioned, e j omega 0, omega being the pulsation, which is 2 pi f0, okay? So e j omega 0 t would give you delta function, which is shifted by f0, delta f minus f0, okay? So here, instead of 1 over 2 e j omega 0 t plus e j minus omega 0 t, okay? So you get delta functions divided by 2. The same thing here, okay? You use them for reference. Let's go now for an example applying the Fourier transform. We have this function xc equal rect t small t over big T, where t absolute value is less than 1 over 2, and which is for t is less than 1 over 2, or t greater than minus over 2, which is this domain over here. The value of rect, which is a port signal, is equal to 1, otherwise it is 0. So outside of this interval, the value is 0. Between minus 1 over 2 and plus 1 over 2, it's equal to 1. So the Fourier transform xf is equal to integral minus infinity to plus infinity xt, which is this function, times exponential minus j to pft dt. Now, since the signal is only represented between minus 1 over 2 and plus 1 over 2, we can bind this interval, like the boundary or the domain of this interval, between minus t over 2 and plus t over 2. So xf is equal to integral minus t over 2 plus t over 2 xt e minus j 2pft dt. All right, so the value of this integral is 1 divided by minus j2pf, because t is the variable, times exponential minus j2pft. This is an integral calculation. If you're not aware of it, okay, you just memorize it, or you need to review integrals. Now, so this is the value, or the sum value of the integral, and it is bound by these 2 points, plus t over 2 minus t over 2. These are the domains of this integral. So we're integrating these two, this function multiplied by the exponential between these 2 values. So we replace right now, for simplicity, 2πf with omega. So you get e minus j omega t over 2 minus e j omega t over 2 divided by minus jw. All right, now we multiplied both of them by minus, so you get a or e gwt e minus jwt over 2 divided by jw. We know that sine theta is equal to e j theta minus e minus j theta over 2j. All right, so let's multiply by 2 the denominator. So you need to balance that by multiplying the numerator also by 2. So you get 2 over omega, and this sum, or this component here, this fraction, which is e j omega t over 2 minus e minus j omega t over 2 divided by 2j, which is the sine theta. All right, so it is equal to t over omega t over 2. Great. Right now we need to reform it, to reshape it in the form of the cardinal sine wave, which is equal to, the cardinal is sine alpha over alpha. This is the form of the cardinal sinusoid. So it's equal to, we need to multiply, we already have w on the denominator, so we need to multiply it by t over 2, and you multiply the numerator also by t over 2, so that we won't change the value. All right, so right now you get 2 times t over 2 divided by omega t over 2 times sine omega t over 2. Now, for the numerator, you cancel 2 because it's in the numerator and the denominator, so you get t times sine wave omega t over 2 divided by omega t over 2, which is the cardinal sinus value. So it is equal to t times sin c, or sinc, if you would call it that, omega t over 2. Great. Now, how to draw it? At first, let's notice something. As t increases, the pulse spreads in the time domain, correct? And becomes wider. But in the frequency domain, when t increases, the pulse, or in the frequency domain, the sin c value shrinks down, it narrows down. So they are inversely proportional. Now, as t decreases, meaning when the pulse in the time domain decreases, then in the frequency domain, the function spreads out. But, of course, again, in the time domain, the function narrows down. So they work opposite to each other. So let's plot the wave. You have, for sine pf over f, because, you know, the form of sin c is sine px over px. So sine pf is equal to 0 for what? You have, for pf is equal to plus minus pi, and for f is equal plus minus 1. Now, so in other words, because we've changed omega to 2pf, 2 is you know, annihilated by the denominator, so you get sine pft divided by pft multiplied by t on the outside. Let's say t is a constant value, so we need to work on pi f. So pi f is equal to plus minus pi, so you get f is equal to 1. Of course, for 0, the sin c is equal to 1. Now, for plus minus pi, okay, the frequency, because this is the axis of the frequency, by the way, this is the axis of the frequency. In other words, this is f over here, and this is xf. So for f is equal to 1 and minus 1, you have an intersection with the x-axis. So it intersects the Sinc over these 2 points. Then the next point would be 2 pi here and minus 2 pi. So if pi plus f equal plus minus 2, the same way. So the next intersection point would be for f is equal to plus 2 and f is equal to minus 2. So on and so forth. Of course, it dies out quickly, but this is the form of the plot of Sinc function. All right. Now, so xt is equal to, if you want to get the inverse function, xt is equal integral minus plus infinity xf e minus j omega df. That's to get the inverse Fourier transform, to get the original function out of the transform itself. All right, so let's do an exercise to get the inverse Fourier transform. So you have xejw is equal to 1 divided by 1 minus 1/2 e minus jw. All right, so the form of this function is close to what? Because if you look back on the chart, this is equivalent to, actually this is the transform of xn is equal a power n un, correct? Where a in this case is actually 1 over 2. That's a equal 1 over 2. So xejw is equal to 1 divided by 1 minus over 2 e minus jw. So xn is equal to 1/2 to the power of n un. This is the original function from which we've gotten the Fourier transform in the example over here. We're going to get, or we're getting actually the reverse function or the original function, which is the one that had transformed into this sum or this value. So this is the value we are restoring back. This is the original signal. All right, first 5 values according to this example. x0, okay, is 1/2 to the power of 0 multiplied by the unit step function, which is just to imply that this function goes from 0 to infinity, but there are no values before n equal 0. x1 is equal to x2 is equal to 1/2 square, x3 is equal to 1/3 square, x4 is equal to 1/4 square, which is 1/16. Causality. So yes, the signal is causal. Why? Because xn is equal to 0 for all n less than 0. So for the causality, yes, the signal has causality, is causal, given that for every n that is less than 0, you have no values for xn. As for stability, yes, the signal is absolutely stable. It's absolutely summable. Why? Because this is a geometric sequence that gives us 1 minus 1 over 2, which is equal to 2. So it is a finite value less than infinity. All right? And given back, yeah, it was minus 1 over 2 e minus j omega, actually, yeah. So for n going to infinity, what happens is that this value narrows down, it converges to 2, so it is a stable signal. It doesn't give infinite values. So this is the final answer for xn, 1/2 to the power of n un. Now let's do another example. So you have this signal xejw is equal to cosine w. We need to compute the inverse DTFT to find the corresponding time domain signal xn. At first, the inverse transform of Fourier is done using this equation, this formula, if you will. xt is equal 1 over t, which is the period, the time spread for the signal, for which we are going to restore the original. Integral minus t over 2, which is half of this time spread, or this domain, or the first boundary, if you will, plus t over 2, the second boundary, xf ej omega t df, or ej 2 pi ft df. Let's start with the t. The period here is between minus pi to plus pi, so in total, this is 2 pi. This is one cycle. You know that the cycle or the period of a function, of a periodic signal, is especially for the sine wave or the cosine wave, is either between trough and trough, peak and peak, or between the first zero and the second zero over here on the axis of t. So xn is equal 1 over big T, which is 2 pi, that's the time spread for the signal, integral from minus pi to plus pi, which is, you know, the two boundaries, from minus pi, the first boundary, to plus pi, the second boundary, x ej omega, which is the function here, or cosine omega, times ej omega n dw, because we are working in the discrete time. So we already know that the cosine w, which is x ejw here, that's the function. Cosine w can be transformed into the exponential format, which is 1/2 ej omega plus e minus j omega. So we replace x ej omega by this sum over here. So xn is equal to 1 over 2 pi integral minus pi plus pi cosine omega ej omega n dw is equal 1 over 4 pi. Why? Because you have 1/2. So it's multiplied by the 2 pi on the outside. Integral minus pi to plus pi ej omega n plus 1. Why? Because you have ej omega multiplied by ej omega n. So you add up the exponent. So it's ej omega, or e to the power j omega plus j omega n, or j omega times 1 plus n, correct? Or n plus 1 plus ej omega n minus 1. The same thing for this element here, e minus j omega times e j omega n is equal to e j omega times 1 minus n, correct? Or I'm sorry, n minus 1 dw. You get 1 over pi integral between minus pi to plus pi ejw n plus 1 plus ejw n minus 1, because the denominator has been multiplied by 2. So 1 over 4 pi e j pi n plus 1, that's the result of the integration, because integral of ejw n plus 1 is 1 over j n plus 1 ejw n plus 1 between pi and minus pi. That's for each one of these two. So the same thing for ejw n minus 1 integrated between pi and minus pi is 1 divided by j n minus 1 times ejw or omega n minus 1 between plus pi minus pi. So let's resolve that. Of course, 1 over 4 pi is a constant kept outside, and multiplying every component, which is the result of this integration, e j pi n minus j pi n plus 1 divided by j n plus 1 plus the second side e j pi n minus 1 divided by j n minus 1. Now we need to multiply the denominator by 2 for these two components. So you have 2 here, 2 here, and we need to compensate that as to not change the value of the equation. So you multiply by 4 the numerator. What you get is 1 over pi multiplied by, if you notice something, ej minus j pi n plus 1 over 2j, that's like saying ej e minus theta, okay, divided by 2j e theta minus ej theta minus e to the power of minus j theta divided by 2j, that's the sine, that's sinus. So we replace that by sine p times n plus 1 divided by n plus 1. The same thing here, e minus j pi n minus 1 divided by 2j. This gives you sine pi n minus 1 and divided by n minus 1, which is left. That's the original signal restored from the cosine omega. Alright, thank you all for watching, and see you next time.